Hi, let us try another example related to the design of reinforced concrete column. In this example, we're going to compare the design steps for various types of column, including the braced and unbraced column, short and slender column, bending in the major axis and the minor axis, and probably we will deal with the design of the biaxial bending column. Since there are a lot to be covered, it is expected that there will be a series of videos covering all types of column. Stay tuned, and without further ado, let us get started. First, let us look at the key plane. This is the ground floor and the roof floor key plane. The dimensions are given. It is stated that all beam size is 150 times 450, whereas the slab thickness 125, and all columns have the dimensions of 300 times 150. This shows the orientations of the column. This will be the major axis, and this will be the minor axis. If you look at the elevations, it shows that this is a double-story structure. The roof floor and the ground floor has the same structural key plane, whereas the first floor will have a separated key plane. The story height are given here, and this shows the first floor key plane. The arrangements of the columns, it will be the same, except that there is a void here. Based on the dimensions of the slab, we know that these are one-way slab, whereas these are two-way slabs. Same goes to the ground floor and the roof floor. This will be the one-way slab, and this will be two-way slabs. Next, we look at the loading acting onto the structure. The loading for the ground floor and the first floor will be the same, 1.2 GK and 2.5 QK. The units are both in kilonewton per meter square. As for the roof floor, the GK is 0.6 kilonewton per meter square, whereas the QK is 0.4 kilonewton per meter square. It is stated that the GK is inclusive of the weight of the beam, slab, brick wall, and columns. That means ultimately the GK given, it will be the total GK. Having the questions understood, now let us look into the sub-questions. The questions ask us to propose the critical load arrangement and determine the type of the loading acting onto a series of columns. We are looking at column A3, B3, C3, and D3. This is column A3, B3, C3, and D3. We are referring to the ground floor column, which is this. You know that later when you need to do the analysis, in order to determine the axial load, we are calculating all the forces on top of the column. There will be two moments to be determined. And one, it will be the joints to the first floor. And number two, it will be the joints with the ground floor. Since the structural key plane, it will be different at the first floor and the ground floor, it will expect different degree of loading in terms of the moment acting onto both ends of column. Next is about the principles of load distributions. We know that these slabs are one-way slab. It is because the Ly per Lx ratio is more than 2.0. Because of that, we will know the load distributions. It will be half of the slab will go here another half will go the other side. As for this slab here, the Ly per Ls ratio is less than 2.0. That means you know that the loads is going to be two-way. And there are two methods for you to calculate the loads. First is by using the yield line method. Second, it will be by referring to the table in British Standard 8110. To make it simple, you can imagine the distributions of the load onto the slab by drawing a 45-degree lines where they meet each other, and this will be the regions where the loads are distributed. Now, because of the load distributions, particularly if you are talking about this beam, you will expect some loading acting on the beam here, but no loads will be acting here, since the loads will be entirely distributed to the longer span. As for the void, there won't be any beam and slab. Thus, theoretically, you will not expect any loads acting at this region. Now, having this understood, we come back to the question. You will need to propose the critical load arrangement and determine the type of the loading acting onto those columns. First, you will need to determine the critical load arrangement. Column, it will be more susceptible to the bending moment. Therefore, in order for you to get the critical load, the top priority shall be given to the moment. Under the setting with the maximum moment, you will need to put the rest of the load carried by the moment to the maximum. This will give you the largest possible moment acting onto the column, and then within that setting, the largest axial loads acting onto the column. Later, when you need to design the column, it will be based on the load as acquired from the critical load arrangement. Let us first deal with the ground floor column A3. We are talking about this column here. Since we do not expect any loads acting onto the beam here, that means we're going to expect one directional bending to the column. From here, you know that it will be uniaxial bending of column A3. Let's say now you view this plan from this side. The structure should look something like this. You expect no loads from the incoming beam, and you also assume there is no load here. Why is it so? It is because when you view from the first floor key plane, this region is a void. As a result, you do not have any load here. By having this side to be the maximum load, that will give you the largest possible moment acting at this end. Because of the UDL here, there will be fixed end moment. However, this side, there is no fixed end moment. Whatever moment happen here will have to be paid by the joint here. Now, it depends on the stiffness of the column with respect to the total stiffness of the joint. Then you are able to determine the moment acting at the column here. Having the maximum load here and zero load here will give you the maximum possible moment. And under this setting, the rest of the loads will have to be at the maximum. What does it mean by the maximum load? We are talking about the ultimate limit states, where both GK and QKs are present. Ultimate limit state will require the factor of safety for the GK and QK 1.35 and 1.5 respectively. As for the minimum load, only GK is present, but the QK is not present. Also, we deal with the ultimate limit state. Therefore, you're going to need this factor of safety of 1.35 for the GK. Now, based on the load arrangement, you know that this column is subjected to uniaxial bending, and the bending, it will be in the major axis. Why is it so? You may refer to the orientations of the column. All the columns have the same orientations. That means column A3 will have this arrangement, and the bending now, it will be in these directions, which is bending towards the major axis. Where else you have no loops here, you have no loops here. That means you don't have any bending in the minor axis. From here, we can conclude that column A3 is a uniaxial load bending in the major axis. Next, you need to determine the critical load arrangement for column B3. This is column B3. Surrounding the columns, these are the regions. We have two one-way slabs and a void. The void here is without any load. Since these two slabs are one-way slab, you will not expect any loads here. Now you're going to see the frame something like this. No beam here. In order to generate the largest moment possible here, that means you're going to have the maximum load here. There will be fixed end moment due to the load here, but no moment on this side. Whatever fixed end moment generated here, it will be absorbed by the joint. Based on the stiffness of the column, with respect to the total stiffness of the joint, you are able to determine the moment taken by the column. Under the setting of the largest possible moments here, the rest of the load, it will be maximum load. You know that when we determine the critical load arrangement in this case, we simply ignore the weight of the beams. For simplicity, since the question here already stated that the GK given is already inclusive of the weights of the beam, slab, brick wall, and the column. Now, even you need to calculate the weight, the critical load arrangement shall end up the same. When the span of the beam are the same, the weight of the beams shall also be the same. Counteracting each other, it will end up to be without any moment. Therefore, this will be the arrangements of the critical load for column B3. Based on the load arrangement, you know that the loads, it will be uniaxial load acting in the major axis. The column arrangement, it will be something like this: 300 here and 150. The bending is in these directions. Therefore, it is only uniaxial bending towards the major axis. Next, we look at column C3. Surrounding the columns, we have the void, one-way slab, and two-way slabs. Take this frame out. It should look something like this. We are talking about this column. Based on the distributions of the load, one-way slab will have no loads distributed to this beam. You will assume half of the slab, the load will go to this side. As for the two-way slab, This shall be the loop distributions. There will be loops acting on this side and also this side. Same goes here. By looking at the key plank here, you want to generate the largest moment as possible. It is either this side maximum load or this side maximum load. Since you have a void here, the maximum possible load on this side will not be greater than what is possible on the other side. Therefore, you know that definitely you are looking into the maximum load on this side. Having the maximum load on this side, to get the largest possible moment into these directions, you will need to minimize the loads acting onto the beam here. No loads from the void, but there will be loads distributed here. Now you're going to make it the minimum loads for this slab. This shall give you the largest possible moment in these directions. Not only that, we will need to look into this frame also. Due to the one-way slab here, there won't be any loops acting onto this beam. To generate largest moment possible in these directions, you will need to make these loads to be maximum. Since this side will carry the loads here, you're going to assume that both slabs here, if you are computing the moment here, to be the maximum load. Now, based on such a load arrangement, you will get moment in the major axis and also moment in the minor axis. Ultimately, it will be the biaxial bending moment. Next, we look at the column D3. This is the columns that we are referring to. Taking out this frame here, this shall be what it looks like. Again, you want to get the largest moment possible. That means one side of the column will be the maximum, while the other side will be the minimum load. How do you decide which should be the maximum and which should be the minimum? Normally, we look at the span. The maximum load should go for the longer span. However, in this case, both spans are the same, so it is up to you. You can have this side maximum or this side maximum. Either way will do. At the end of the day, you will get the same moment. Having these directions settled, we look into this frame here. Since you have no beam here and no slab here, that means this side of the columns is not contributing any load. To get the largest moment as possible, you will need to make these beams taking the maximum UDL load. For that, you will need the maximum loads for the slab here and also maximum load for the slab here. At the end of the day, you will expect the bending in the major axis and also bending in the minor axis. So, this column, it will be the biaxial loading column. In summary, column A3 and B3, it will be uniaxial bending to the major axis. Column C3 and D3, it will be biaxial bending on both axes. So later, when you need to design the reinforcements for those columns, especially on the dimension side, you will need to be extra careful whether the bending is towards the major axis or the minor axis. The main differences between the bendings in the major and the minor axis, it will be the effective depth later you use to calculate the moment resistance of the column. The larger effective depth will give you greater resistance. This gives you an idea for you to decide the orientations of the column. For economical solutions, if you anticipate the moments will be larger in certain directions, it is always a good practice for you to have that directions to be with the major axis. This can save you a lot of reinforcement. And then the calculation steps for the uniaxial bending and the biaxial bending shall vary slightly, which we're going to discuss about this in our future videos. Now, as far as this questions is concerned, we know now under different circumstances, the column may be subjected to different types of load, and different types of load will result in the different design outcome of the column design.